All right, well, here's our final lecture in chapter 4, and I'm continuing here with the redox rules or the oxidation state rules. And here's the table for it, so just as a reminder. And then that's going to lead into a problem like this where you're asked to assign oxidation numbers to each of the atoms in the following chemical species. So in carbon dioxide, you have a structure like this. We could say which is the most electronegative element here. It's oxygen, so these electrons all go to the oxygens. The oxygens end up with 8 electrons around each of them. They ended up, as a result of that, having a -2 charge. The carbon ends up with no electrons around it, and therefore, being in a group 4 element, 4 minus 0 is a 4 plus charge. But I don't necessarily like that. You go back to the previous slide, you'll see that the rules are for oxygen. If it's an element like in O2, then it will have an oxidation state of 0. If it's in a peroxide, which has an oxygen-oxygen bond, like in hydrogen peroxide, then the oxidation state of the oxygens is a -1. But every other molecule you'll see, it'll be in a -2 oxidation state. The rules also clearly state that the sum of the oxidation states will add up to the charge of the species. Carbon dioxide is neutral, and therefore, because the oxygens have each -2, the carbon needs to be a +4 oxidation state. In sulfur hexafluoride, we don't need to draw structures for this. I'm just doing it just because, but you have a structure like this. Each of the fluorines is going to have 3 lone pairs. Fluorine is the most electronegative element, so both of the bonded electrons go to the fluorine, which gives it, each of the 6 of those would have 8 valence electrons. Fluorine is in group 7. 7 minus those 8 electrons, is going to end up with a -1. So you get those, those fluorines, each with a -1. It's neutral, so the sulfur ends up with a +6. I'm not going to do the rest of the fluorines, but there you go. The rules also state that fluorine is always -1 unless it's in its elemental form. And so therefore the sulfur must be, in that case, a +6 again. Next we have the nitrate. So NO3 is going to have a structure. I'm not going to draw its proper structure according to Vesper theory, just for simplicity, but it will look like this. Now, overall, this has a negative charge. We look at formal charges. We'd get those formal charges there in this particular resonance structure for the nitrate ion. All right, when we look at the oxidation states, though, we could say those electrons all go to the oxygens, or we could just use the rules and say the oxygens are not in peroxide, so they're going to be -2 for each. And so the oxidation states will be in red here. Overall, this has to add up to a -1. So one way to do this is to say there's 3 oxygens, there's 1 nitrogen, and this is like an algebraic equation. They're going to add up to -1. Since the oxygens by definition here have to be a -2, you can substitute that into that equation. So -6 plus n equals -1. Add 6 to both sides. You get n is a +5 oxidation state. So again, you see the oxidation states and the formal charges don't match by magnitude. Sometimes they don't even match by sign, but it is what it is. Actually, just another example of that, carbon monoxide has this structure. The carbon has a -1 formal charge while the oxygen has a +1 formal charge. All right. Electronegativity-wise, again, carbon's 2.55, oxygen's 3.44. So you have a dipole moment going in the direction of the oxygen, meaning the oxygen should be partially negative and the carbon should be partially positive, which, seems counterintuitive here. When we look at oxidation states, again, oxygen is more electronegative, so we have 1, 2, 3 sets of electrons all going to the oxygen. You end up with these. So again, the oxygen is going to be a 2- charge, and the carbon is going to end up with a 4- those two dots and be a +2 charge, or a 2+ charge, I should say. So the oxidation state of the carbon is actually +2 and -2 for the oxygen. It follows those rules. Oxygen is always -2, so therefore the carbon has to be +2 because carbon monoxide is neutral. So again, the formal charges and the oxidation states are not matching up here, but that's just what it is. And carbon monoxide being used in reactions will follow these oxidation states with the flow of electrons from whatever it's reacting with. All right, the next one, Fe3O4. We've got 3 irons and 4 oxygens. This is an ionic compound, but overall it's neutral. So you're going to add those up to 0. Again, we're going to follow the table that says that oxygen is going to always be -2 unless it's a peroxide or elemental form, and it's neither of those. So we get 3 irons plus 4 oxygens, which will each be -2, and that's going to add up to 0. So 3 irons minus 8 will be 0, so 3 irons will be +8, which means these irons have an oxidation state of +8/3, which is really weird. That's another distinguishing feature with oxidation states versus formal charges, is that you can have, at least in theory, these charges that are weird fractions. Now, in reality, if we were to learn more about the structure and bonding of Fe3O4, we would see that based on how that works, that 2 of the iron atoms have a charge of +3, and another one has a charge of a +2, or I should say oxidation states, which if you divide the sum of those, 3 + 3 + 2, by those 3 atoms, on average, they are a +8/3. But so you're not getting a third of a charge in reality, or a third of an oxidation state, but that's how it works. And so if just given a formula, you'll say the average of those atoms is 8/3. All right, now oxidizing agents versus reducing agents. Oxidizing agents are chemicals that oxidize other species, and in turn, because they're oxidizing something, they're giving oxygen to something. So something's being oxidized. And you remember oil rig. All right. Oil rig states that oxidation is loss of electrons. It's also a loss of hydrogens. But it's also gaining oxygens. All right. And so the thing that's being oxidized is gaining oxygens, whereas the other chemicals are losing oxygen. The oxidizing agent is losing oxygens, so it's being reduced. So chemicals that oxidize other species are oxidizing agents, but in turn, they're being reduced. And the same will be true for the reducing agents. but just in reverse. So these are chemicals that cause other chemicals to be reduced. And in turn get oxidized. All right, metallurgy, the process of producing a metal from its ore, always involves redox reactions. In the metallurgy of galena, PbS, which is therefore lead 2 sulfide, the principal lead-containing ore, the first step is the conversion of lead sulfide to its oxide, a process called roasting. So we see 2 PbS solids react with 3 oxygen gas molecules to produce the 2 formula units of lead 2 oxide and 2 molecules of sulfur dioxide gas. The oxide is then treated with carbon monoxide to produce the free metal lead. For each reaction above, identify the atoms that are oxidized and reduced and specify the oxidizing and reducing agents. All right, so let me get rid of that stuff. Well, we have lead ultimately coming from this PbS, the galena. All right, the oxidation state of lead is 0. The oxidation state of oxygen is 0, because those are elemental forms of those elements. Okay, so we still need to look at what's actually being oxidized and what's being reduced. Well, the lead in galena has 0 bonds to oxygen. It ends up in the first process having bonds to oxygen. So you might think that's being oxidized. However, it's not. And part of the reason is that sulfur is in the same group of the periodic table as oxygen. So you would expect sulfur and oxygen to do the same thing or to have similar properties in redox reactions, and that would be true. The galena is an ionic compound, and in this, the lead has a 2+ charge and the sulfur has a 2-. And the same is true for the lead 2 oxide. You have a 2+ charge on lead and a 2- charge on the oxygen. These being ionic compounds, their oxidation states will match their ionic charges. So nothing is, I should say the lead is not being reduced. Now or oxidized. When we go to the sulfur dioxide, well, we have a sulfur plus 2 oxygens is going to add up to a sum of 0 because SO2 is a neutral compound. This is a molecular compound because both sulfur and oxygen are nonmetals. So we don't have charges here necessarily. Following the rules, oxygen is always a -2 oxidation state unless it's a peroxide or in the elemental form, and this is sulfur dioxide, not sulfur peroxide. And so it's sulfur plus 2 times -2 being 0, so sulfur minus 4 is 0, meaning the sulfur is a +4 oxidation state, and the oxygen is a -2 oxidation state. All right, so in fact, the sulfur went from a -2 to a +4. Going from -2 to +4 means it must be losing 6 electrons, because 4 minus 6 would be -2. The sulfur losing electrons means that the sulfur is actually oxidized. The sulfur is gaining bonds to oxygen, so that should make sense. It goes from 0 bonds to oxygen. Now there's at least 2 atoms of oxygen is now bonded to. The oxygen goes from a 0 to a -2, so it gained electrons. Furthermore, you could say the oxygens lost bonds to oxygen. It was a double bond, and then in sulfur dioxide, you end up with a structure like this. and the sulfur has 3 bonds to oxygens, or the oxygens have no bonds to oxygens, so they get reduced. The lead, on the other hand, is not oxidized or reduced. All right, in this first reaction, because the sulfur is being oxidized, it's causing the reduction of the oxygen, so it's the reducing agent. And by the way, that reducing agent is the whole compound, while the sulfur in it is the piece getting oxidized. The oxygen, which is very common, is the oxidizing agent. It is oxygen after all. So that whole molecule is the oxidizing agent. It's getting reduced. The oxygen atoms are both reduced there. In the bottom reaction, we go from the PbO, which has a +2 and a -2 oxidation state for those atoms. Carbon monoxide, we already did, has the same values. All right, and carbon dioxide, we already did that, +4 and -2 for those oxidation states. The lead goes from +2 to 0, so we added electrons to it. That means it's reduced. It also loses a bond to oxygen. So this is reduced. The oxygen stays as a -2 throughout, so we're not going to talk about that. The carbon goes from a +2 to a +4. It gains 1 oxygen atom. It goes from 3 bonds to oxygen to 4 bonds of oxygen. You may remember in class when I talked about incomplete combustions will create carbon monoxide, while complete combustion creates CO2. It's because you have more oxygen gas there, and so the carbon can just gain more bonds to oxygen as much as it possibly can, which is those 4. So the carbon is oxidized, the oxygen is untouched, the galena, or I'm sorry, not the galena, thinking of the top reaction there, the PbO is therefore the oxidizing agent. It provides the oxygen to the carbon monoxide, which is the reducing agent. So you'll see that the compound containing the element that gets oxidized is always the reducing agent. The compound containing the element getting reduced is always the oxidizing agent. So that is kind of confusing. So you really need to make sure you're understanding what the definition of oxidation is, what the definition of reduction is, and then what are the definitions of oxidizing agents and reducing agents. Consider the following reaction. Now this is under balancing redox reactions. Assign oxidation states to each atom. Well, the first bit is that copper is in the solid state, so it's in its elemental form, so has 0 for its oxidation state, as does the silver over here. The silver plus is going to have a +1 oxidation state, and the copper 2 plus is going to have a +2 oxidation state. What you'll see is that the atoms are balanced, but the charges are not. And that means that in reality, what we don't write in these equations are the electrons. The electrons are unbalanced. So this still violates the law of conservation of mass, the law of conservation of energy, the law of conservation of charges. You could talk about any of that stuff. They're not balanced. And you go 0 plus 1 is +1 and 0 plus 2 is +2. So they're unbalanced. Since copper has been oxidized by losing 2 electrons, all right, so this losing electrons causes the copper to be oxidized. Silver gains an electron, and so it is reduced. The charge goes from positive to neutral. It goes down. It's reduced. Since copper has been oxidized by losing 2 electrons and silver has been reduced by gaining just 1 electron, right? So -2 electrons plus 1 electron there. The equation above is not balanced. Below, though, is. All right, again, if we look at it this way, there's copper with a 0, the silver with a 0. We have 2 silver, 1 plus ions, so 2 times a plus 1. And then on the right side, we have a 1 copper atom that has a plus 2 oxidation state. So 0 plus 2 is 2, and 0 plus 2 is also 2. 2 equals 2, so this is balanced. So in reality, the redox reaction is not going to be as shown above, but down below, where we have copper metal plus 2 silver ions will react in the redox reaction to give 2 silver atoms plus 1 copper 2 plus ion. All right, so now if we have these two reactions, we have iron metal and copper metal. Those are those elements. We have a copper 2 plus, and we have an iron 2 plus charge, I should say. And so those are balanced because the charges are not any different. We don't have to do anything special there. With potassium permanganate and iron 2 chloride, we end up, you might want to split this up into the ions. Notice I have Mn2 plus and Fe3 plus as the products. That's not balanced by atoms at all. And the reason is I didn't want to give too much away here. But we might split this up into K plus MnO4 minus plus Fe2 plus and 2 Cl minuses. Those will combine in water to yield Mn2 plus Fe3 plus. So it turns out that I don't have to worry about the chlorine. That's going to come later. But when we're balancing this, let's just look at the charges. We have plus 1, minus 1, that adds up to 0. Plus 2, minus 1, but there's 2 of them, so those add up to 0. And then on the right side, we have a 2 plus and a 3 plus. Those add up to 5, so it's not balanced here. So what do we do? Well, we're going to use the half reaction method. First rule there is to split the reaction into 2 half reactions, one half including only the element being oxidized and the other half being the element reduced. Balance the element being oxidized or reduced in each of those half reactions first. And then in each half reaction, balance oxygen atoms by adding water into the reaction. And I'll show this in the example. Then in each half reaction, balance hydrogen atoms by adding H plus ions or acid into the reaction. In each half reaction, balance charges by adding electrons into the reaction. Add coefficients to the half reactions as necessary to cancel out electrons from each side of the equation. Because ultimately the reaction will never show electrons because they should always be balanced. And then finally, step 7, combine the 2 half reactions and cancel out chemicals that are on both sides of the equation. So for the first of those two, I've done the half reaction method for them. I have what we started with before, iron and copper 2 plus, going to iron 2 plus and copper metal. Right, that was already balanced. We have iron losing 2 electrons to form that Fe2 plus. We have copper gaining 2 electrons to reduce into the copper metal. All right, the atoms are balanced. The charges are balanced, right? 2 plus and 2 minus add up to 0, just like the copper is. 0 over here and 2 plus and 2 minus, those are balanced. So we don't have to add anything. We don't have to add oxygen because I don't see oxygen anywhere up here. And we don't have to add water or acid or anything because the atoms are all balanced. Everything we see there is balanced. For the other reaction, though, we have oxygen on the left but not on the right. We have chlorine on the left but not the right. So what do? Well, again, we're going to split this up into the half reactions. All right, I'm going to take the KMnO4 and we're going to make that go to Mn2 plus. Well, and we can even get rid of the potassium. It doesn't really matter And then because we're getting rid of it, it's MnO4 minus going to Mn2 plus. And then we're also going to take the FeCl2 and have that go to the Fe3 plus. But again, I actually can ignore that Cl2 and say this is iron 2 plus going to Fe3 plus. All right, so there we've done that. Now we need to balance the elements being oxidized or reduced, the irons and the manganese and irons. We have one manganese on each side. We have one iron on each side. Those are balanced, so that's fine. The next would be, well, we got to balance out oxygens, and it was we do that by adding water. So in this half reaction, we have 4 oxygen atoms on the left and none on the right. Well, water has 1 oxygen, so we need 4 water molecules. We're going to add that to the right side. So MnO4 minus will go to Mn2 plus and 4 water molecules. All right, so now the oxygens are balanced. Well, now we've added hydrogen into the mix, so we got to balance those. There's 8 hydrogens because of 4 water molecules. And so we're going to add that to the other side. 8 H pluses plus MnO4 minus will yield Mn2 plus 4 waters. So now the hydrogens are balanced, the oxygens are balanced, and the manganeses are balanced. The last step is to balance the charges. So we have a +8 plus a -1. That adds up to a +7. On the right side, we have a +2 and then a +0. So what we can do is add 5 electrons. And those electrons are going to go on the left. All right, so -5, because there's 5 electrons and they're negatively charged, 7 minus 5 is +2. So those are now balanced. All right, this is a balanced half reaction for the manganese. Let's look at the manganese and see what's actually happening here. It goes to this Mn2 plus, all right, from an MnO4 minus. All right, the manganese plus the 4 oxygens have to add up to -1. So manganese plus 4 times -2 is -1. So manganese minus 8 is -1. Add 8 to both sides, and you end up with the manganese having an initial oxidation state of +7. And it goes from +7 to +2. All right, and right there we see there's 5 electrons. But don't do it this way. Don't start with this and just say, well, it's going to add 5 electrons. Make sure you do the water, then the hydrogen ions, and then add the electrons, because there's could be other things in there you got to consider. All right. Again, 7 plus 5 electrons does go to 2. For the other half reaction, well, the atoms are balanced. The things that are not are the electrons. So what do we do here? Well, we add 1 electron, because a 3 plus and a 1 minus add up to a 2 plus, and that's it. All right. So we've balanced both half reactions by atoms and by charge, and then we combine them. But you'll see that we need to cancel out the electrons first. We have 1 electron as a product from iron getting oxidized, and then we have 5 electrons reducing the manganese. Well, the electrons need to be totally balanced, so we need ultimately 5 times this whole set of reactants. So we're going to have 5 electrons plus 8 hydrogen ions plus the manganate ion, yielding manganese 2 plus ion and 4 waters. Then we're going to add to that 5 Fe2 pluses, yielding 5 Fe3 3 pluses and 5 electrons. We're going to add those up, and you get 5 electrons plus 8 H pluses plus a manganate ion plus 5 Fe2 pluses. Those will yield the Mn2 plus 4 waters plus 5 Fe3 pluses plus 5 electrons. Well, there's 5 electrons on both sides, so those cancel out. That's awesome. Nothing else is on both sides in this case. There are reactions where this half reaction we might have to add water or acid to balance those things out, but we didn't have to here. So this is, in a sense, the complete reaction. We see that there's an 8 plus a negative 1 plus 5 times positive 2 on the left side of the equation for the charges. There's a plus 2 plus 0 plus 5 times plus 3 for the charges on the right. 8 minus 1 is 7 plus 10 adds up to a positive 17 charge on the left. And we have a 2 plus a 15, which is also a positive 17 on the right. So there's our balanced equation. It balances the electrons, it balances the atoms, the charges, everything. Just to point it out, we have 8 hydrogens, a manganese, 4 oxygens, and then 4 times 1 is 4, 5 irons, There's your balanced equation. So it's 8H plus MnO4 minus plus 5 Fe2 pluses will yield Mn2 plus 4H2O plus 5 Fe3 plus. Now remember, we started though with FeCl2 and KMnO4. Something just fell behind me in the room. I don't know what it was. So what is that? Well, maybe we add, in reality, 8 HCl plus KMnO4 plus 5 FeCl2. All right. HCl gives us the H pluses. FeCl2 is still there. We get the Fe2 plus. And maybe that yields manganese 2 chloride, 4 waters. And we're still missing the potassium. And then 5 FeCl3s. The interesting thing to note here is that we look at the hydrogens. There's 8. We look at the manganese. There's 1. The oxygens, 4 and 4. When we look at the potassiums, we have 1 and 0. When we look at the chlorines, we have 8 plus 10 is 18 versus 2, and then 5 times 3 is 15. That's 17. Okay, so we're off by 1, which means that in essence, we also are making KCl. There's our 1 potassium, there's our 1 extra chlorine. So in this reaction, you're actually combining 8 molecules of acid, HCl, to 1 formula unit of KMnO4 and 5 formula units of FeCl2. That'll make 1 formula unit of manganese 2 chloride, 4 molecules of water, 5 formula units of FeCl3, and 1 formula unit of KCl. Normally when we do these balancing redox reactions, we don't go into that. Normally we wouldn't even show the Cl or the K there. You just write the ions like I've done down there, just to avoid the confusion. And the K started as a +1, the Cl always is a -1, or it started off as a -1 here, it started off as a -1 there. So they didn't get oxidized or reduced, but the iron and the manganese did, so that's why we had those. And then the water was added and the HCl was added to balance out charges and everything else. All right, subtypes of redox reactions. There's 5 here. Combination reactions, decomposition reactions, combustion reactions, single replacement reactions, and double replacement reactions. And I just now noticed that the slide numbers don't match in what they should be. And the reason for that was when I was making the file here to make this video, I deleted the slides that I had already taught in class. So there's 26 slides that are left or total in this lecture. So really it's 10 out of 26, but originally it was 84 and I didn't go in to change that. All right, in combination reactions, we see we have an example here of sodium and chlorine. Those are both in their elemental form, so they have oxidation states of 0. They combine to make sodium chloride, which has these charges. It's an ionic compound. The sodium goes from neutral to positive, so it's oxidized. The chlorine goes from 0 to negative, so it's reduced. But it's a combination reaction because you're going from 2 units to 1. All right, and then the bottom example, I have hydrogen gas and oxygen gas combining with heat. The delta symbol there, capital delta, means we're heating it, we're changing the temperature of the reaction. Like any fire needs a spark, and hydrogen combining with oxygen makes a fire. And so that's why we have that delta symbol there. And they make liquid water. So you're going from 2 elements to a compound. I should also add that combining 2 or more chemicals into one, the product will always be more complex than the reactants. So you could go from 2 compounds to a more complex compound. You could go from a compound in an element to a complex compound, or you could go from 2 elements to a compound. It's always going to be more complex as a result of the combination reaction. Decomposition reactions are the opposite. It's where you're breaking down a chemical into simpler substances. All right, so I have 2 examples here. I have the opposite of the previous, where I have water breaking down with electricity to hydrogen gas and oxygen gas. So this one creates 2 elements. Both of those are simpler than the molecular compound water. Hydrogen peroxide with light can break down to form the compound water and oxygen gas. Water is simpler than hydrogen peroxide because it has fewer atoms. That's really all there is to it. It has the same elements, obviously, but there's just fewer of them, fewer atoms in total, so it's simpler than the hydrogen peroxide, and we get the elemental oxygen out of it. And I wanted to point out that we will often say decomposition reactions make elements, but that's not always true. You can decompose things where no elements are made. You can go from complex to 2 compounds that are less complex, or a compound to a simpler compound in an element, or a compound into 2 elements. But you cannot break down elements. All right, we have combustion reactions. So these are some fuel. Generally speaking, we're going to talk about it being hydrocarbons or organic molecules. Things with carbon in them will combine with oxygen to make carbon dioxide and water as products. All right, that's not always true. I talked about that before when we were balancing equations. Like I had the ammonium dichromate compound. When that one ignites, it doesn't actually use oxygen. It has oxygen within it, and it didn't just create CO2 and water. It created nitrogen gas. So some combustion reactions make other gases, but simplifying it, we say, oh, every fire needs a fuel, which will be these organic molecules on the left. They need oxygen, and they need some heat or bit of energy to get them going. It's really kind of a half-truth. It just depends. It's, again, some compounds have enough oxygen within them to change their nature. They will oxidize within. The carbon actually goes here from a -4 oxidation state. The hydrogens are +1. In CO2, it ends up as a +4 in -2. So the carbon got oxidized there. And same thing in octane, it gets oxidized. And I'm not going to do the math there just to save time. There's single replacement reactions where we take an elemental metal, usually, and we take an ionic compound, and they're going to react in water as an aqueous solution, essentially. And the two metals, silver, in this case silver and copper, are going to switch places. Copper goes from a 0 oxidation state and silver from a +1. And then they're going to end up with silver as a 0, and a copper is actually a +2 oxidation state. All right. Notice the nitrate is conserved here. And this is not a balanced equation. I was not trying to do that. I was just showing a single replacement reaction. But you're singly replacing something. An element is replacing another element, two metals, right? The silver and copper are both metals. Here I have zinc as an element, and in this case, hydrogen. It's not a metal, but it can be replaced. So we can do that. Now I'm going to say this one is highly polar, or at least moderately polar, so it's going to happen. HCl is a strong acid, so 100% of the molecules will dissociate like this. So the zinc will then swoop into the chloride and make ZnCl2, and then the hydrogens will actually combine to make hydrogen gas. You're going to an elemental form here, an elemental form over there. You have a molecular compound here, and this is actually ionic. There's also double replacement reactions where both compounds are ionic and both products are ionic. No elements involved here. Barium nitrate is soluble in water. Potassium sulfate, also soluble in water. You get a product that's aqueous and a product that is insoluble. Double replacement reactions require this. They are also known as precipitation reactions. All right. In this case, the barium and the potassium switch places. We have barium nitrate and potassium sulfate, and we end up with barium sulfate and potassium nitrate. And you know what? Let me change the color of the potassium so this is a little more sensical. So we had gray and blue and red and green, and we end up with gray and green and red and blue. Let's do the same thing down below. We had lead, There's the other lead. We had a nitrate. They're no longer together. The lead and the potassium have switched places, and the iodine has also, we could look at it either way, but because metals are switching to two compounds, we call that a double replacement reaction. And again, these require one of the products being insoluble in water, while the rest of them are soluble in water. Aqueous, 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 aqueous. All right, we can follow something like this called an activity series to see which metals are more likely to do replacing. The higher up in the activity series, like lithium here, the more active the element is. Therefore, it's most easily oxidized. It has the strongest tendency to lose electrons. Whereas at the bottom, they're the least reactive. You notice it's gold. Gold is known for not being reactive, and so it follows in the activity series that it is at the very bottom of it. They're most difficult to oxidize. They have the least tendency to lose electrons. Or in other words, when we use the activity series in a double replacement reaction, if we had lithium and potassium, it might be better for a single replacement reaction. You'd want to compare the activity of the elements in here. We had, again, zinc plus HCl to make zinc chloride and hydrogen gas. All right, so let's find those. We have zinc, and actually hydrogen is right there. Zinc is above the hydrogen, which means it's willing to do that. On the other side, if I just started with zinc chloride and tried to react it with hydrogen gas, hydrogen cannot replace the zinc there. This does not create zinc and HCl because the hydrogen is lower in the activity series than zinc, so that reaction will not work. So you can, take a chart like this and just use that information to see if that single replacement reaction will even work. Use solubility charts to see if the double replacement reactions will work. All right, the last bit here in chapter 4 has to deal with concentrations of solutions. The major one is molarity, and molarity is measured in moles of solute divided by the volume of solution. And the volume of the solution specifically will be in liters, while the moles of solute will just be in moles. So you're measuring moles per liter for that. Molality and normality are not in your book, but they're in lots of general chemistry books, so I've included them here. You're not going to have to do work for them, but I did want to expose you to them. Molarity has the capital M as a symbol. Molality has a lowercase italicized m, whereas mass is just a lowercase regular m. And then normality has that capital N for its symbol. Molality is the moles of solute per kilogram, or the mass, I should say, of solvent. And again, the moles of solute will be measured in moles, obviously, and the mass of solute is actually going to be in kilograms. So it's moles per kilogram. Notice the difference. Molarity is the volume of the solution, while molality is the mass of the solvent. Most concentrations use the whole solution, but molality is a unique one where it uses mass of the solvent. The value of molality is that it's really simple. It's simpler than molarity. If I mix water and ethanol and try to make a solution, I could measure the mass. Let's say the solvent is going to be ethanol. Now let's say actually the solvent will be water. I'm adding a little bit of ethanol to a lot of water. I could measure the molarity of the ethanol by measuring the mass of the ethanol, dividing by its molar mass to give me the moles of it. And then I mix the two together to get the volume of the solution. Let's say they add up to 100 milliliters. You just divide by 0.1 to get the molarity. The moles of the ethanol divided by 0.1 would give you its molarity. The problem, though, is I can't just say, well, add 50 milliliters of ethanol to 100 milliliters of water, and you'll have 150 milliliters or 0.15 liters of solution. Because it turns out that solutions don't combine volumes additively. Volume is not additive. So although it's 50 milliliters of ethanol and 100 milliliters of water, the final volume might end up being just 140 or 145. It might be close. It might be 149. Or it might be bigger. It might be 155 or 160, even though you've added only 50 and 100. And the reason is that there's interactions between molecules that cause them to either compress together or spread out. It's similar to the idea or the fact that water expands as it freezes. At 4 degrees Celsius, water is its most dense. So let's say we take tap water at room temperature and we cool it down, we get it to 4 degrees Celsius. During that process, the water molecules are getting closer and closer and closer and closer together. The mass is not changing, but the volume is a little bit. As you get to that 4 degrees Celsius, they get as close as they're ever going to get. If you keep cooling it below 4 degrees Celsius, as it's going from 4 to 0, the molecules actually will start to expand, spread out again even more. And they do so more quickly than it was compressing above 4. And so when you get to 0 and the water freezes, the density of the ice is enough less than water that it floats on top of the liquid water. The volume of the ice is not the same as the volume of the liquid water at, let's say, 4 degrees Celsius or 5 degrees Celsius. It might be the same as somewhere else, but I don't know. And so volume for even a pure substance isn't necessarily quantitative or the same because it can be temperature dependent. Likewise, for solutions, when you're mixing two things together, their volumes aren't necessarily going to add together properly. I could give you an example. Let's say you have a box. Let's say a shoebox, and you put in the shoebox some ball pit balls. If you added up the volume of the ball pit balls and you added up or calculated the volume of one ball pit ball and then figured out how many would fit in the box, and you added the volume of each of those balls together, and then you calculated the volume of the box by measuring its dimensions, you would see that they're not the same. The balls will add up to a smaller volume than the box. Why? Because they're not, the same rectangular prism. There's gaps where there's no ball pit balls touching each other. I could add water into that to fill those gaps in a sense. And same kind of principles are going on with when you mix ethanol and water. They're not mixing perfectly. Long story now short, molality is better in some ways than molarity because all I have to do is measure the mass of the solvent. I just get a bit of solvent, measure its mass, add the solute to it, which you get the moles of it by measuring its mass, and then you mix them together. You get the concentration in molality by doing that. Another issue with molarity is that because solutions can change their volume at different temperatures, molarity is temperature dependent. So if we tell you when something in lab is, let's say, 5 molar, well, it's 5 molar at, let's say, room temperature. But if you used it at 60 degrees Celsius, which is well above room temperature, the liquid's going to expand. When you heat up water, it gets, above 4 degrees Celsius, it gets the molecules get farther and farther apart. They expand. Eventually, they expand enough where they turn into the gas. But before that, it's expanding, so the volume is going up, the mass is staying the same, and since the volume is going up, the molarity is changing. Even though you haven't changed the amount of solute in there, molarity can change just based on temperature of the solution, whereas molality is unaffected by temperature. And then finally, normality is equivalence per liter of solution. Equivalence is kind of like a quote-unquote thing. And it's relative to moles, but it represents how many times a chemical can react or how many electrons it is going to give up or accept in a redox reaction. Like the manganese had 5. So one manganese has an equivalence of 5 because it takes 5 electrons. All right, so we'll see examples of this in the next slides here. We have HCl. I have the molar mass. For HCl is 36.5, whereas sulfuric acid is 98. The equivalent mass, because HCl has 1 acidic proton while sulfuric acid has 2, meaning if I had 36.5 grams of HCl, I have a mole of HCl. So it'll react 1 molar times, 1 mole of reactions, Avogadro's number of reactions if I have 36.5 grams of HCl. If I have 49.5 grams, sorry, not 49.5, but 49 grams of sulfuric acid, I can get 1 reaction out of it. Because I have half a mole of sulfuric acid, and that half has each 2 moles of hydrogen atoms that are acidic. It can react twice as often as HCl, so you need 49 grams of sulfuric acid to do as much as 36.5 grams of HCl. So we see that a 1 molar solution of HCl has a normality of 1 normal, and a 1 molar solution of sulfuric acid actually has a normality of 2 because each molecule can react twice. Same thing for sodium hydroxide and calcium hydroxide, which are bases. The molar mass of sodium hydroxide is 40, for calcium hydroxide 74. So if I had a mole of sodium hydroxide, its equivalent mass is 1. It uses 1 hydroxide versus calcium hydroxide reacting twice. So if I had 74 grams of calcium hydroxide, it'll react with 2 moles of a base versus 40 grams of sodium hydroxide would react with only 1 mole. Or in other words, I could say I need 80 grams of this to react with as much as 74 grams of the calcium hydroxide. So 1 molar solutions of sodium hydroxide are also 1 normal. Calcium hydroxides, you have 1 molar solutions are also 2 normal. And this will come into play like if I have HCl and I'm reacting it with sodium hydroxide, those are going to react in a 1-to-1 ratio and create H2O and NaCl. But if I take sulfuric acid and react it with sodium hydroxide, I need twice as much because this has 2 equivalents while this has 1. So I would need 2 sodium hydroxides to make water and Na2SO4. Or I could say I have HCl plus calcium hydroxide. I have 2 equivalents there versus 1 here, so I need 2 HCl's for that. And that's going to make calcium chloride, again, water. So that's molarity versus normality. All right, dilute versus concentrated solutions. Here I have a dilute solution. Usually we consider dilute solutions less than 1 molar, while concentrated solutions, like on the far right, those are going to be greater than 1 molar for concentrated solutions. Now, there's another way of talking about concentrated solutions. I could say a concentrated solution is the same as a saturated solution, and a saturated solution is one that has the maximum amount of solute dissolved. Now, that is a little bit of a weird term, and the reason is because this is representing comparative concentrations. There's dilute, and then these are more concentrated than the dilute. I could say this is more concentrated than the 2 to its left, but it's not a concentrated solution. If I say something is a concentrated solution, I mean it's saturated and you can't get anything more in there. But if I say it's concentrated relative to something else, I just mean it has more solute than the other one. Here's another example where we'd have concentrated going down to dilute solutions. Calculate the molarity of a solution prepared by dissolving 11.5 grams of sodium hydroxide in enough water to make 1.5 liters of solution. So first of all, because we have sodium hydroxide as our substance and we have a mass of it, and we're asked for molarity, molarity is equal to the moles per liter. Moles divided by the volume in moles per liter. So if we have grams, mass is the same as the moles of a substance. I'm sorry, I don't want to do it that way. I should start with the moles of a substance are equal to the mass of it divided by the molar mass. So the molarity of a substance your book actually does it like this, molar mass like that. The molarity is actually going to be this fraction substituted into here, mass divided by molar mass divided by volume. This is going to be mass divided by molar mass times volume when we simplify that expression. Well, we have the mass is 11.5 grams. We have the volume is 1.5 liters. We don't have yet the molar mass, but the molar mass of sodium hydroxide I can give you is 39.997 grams per mole. You can get those values from the periodic table by adding 1 sodium, 1 oxygen, and 1 hydrogen together. All right, grams cancel out. We have moles here in the denominator of that, but it's also in this greater denominator, which puts it up in the numerator. So we end up with moles per liter there. So 11.5 divided by 39.997 divided by 1.5 is going to give some number. I don't know off the top of my head. I got to get my calculator out to do that. But if we estimate it, let's say 10 divided by 40 would be 1/4, divided by 1.5, which is divided by 3/2, we take 1/4 times 2/3, and we get 1/6. So we should end up with about 0.167. All right, doing the math on my calculator here, 11.5 divided by 39.997 divided by 1.5. We actually get the molarity here of the solution equals 0.19168, but this has 3 sig figs, and so does that. So 1916 becomes 192 moles per liter. I said 1.167. That was an estimate where I had rounded that down to 10 to simplify it, and that's why it's a little bit smaller. So it's a reasonable answer there. To analyze the alcohol content of a certain wine, a chemist needs a liter of an aqueous 0.2 molar potassium dichromate solution. How much solid potassium dichromate must be weighed out to make this solution? Well, again, we need a molarity there. That means moles per liter. And it says how much must be weighed out. So we need ultimately to know the mass. If we go back to that previous equation, the molarity is mass divided by molar mass times volume. We can use that to figure out how much mass we need. Well, we need the molarity times the molar mass times the volume, and that'll equal the mass. We have the molarity, 0.200 molar, which is moles per liter, times the molar mass. Well, we got to find the molar mass for potassium dichromate. You get that again from the periodic table. And that comes out to, for the potassium dichromate, you have 2 potassiums, 2 chromiums, and 7 oxygens. It comes out to 294.181 grams per mole. So you put that into the equation, 294.181 grams per mole. And then finally, the volume, it says we need 1 liter. Well, the liters cancel out, the moles cancel out, and we're left with just grams. All right, so 294.181 times 0.2. Let's say 300 times 1/5. That'd be 300 over 5, which is 60. So it should be about 60. And then we multiply by 1, so it's 60. This ends up being, I'm sorry, that's not a capital M, a lowercase m for mass equals 58.836. We have 3 sig figs, so 58.8 grams of potassium dichromate. Take that, dissolve it in a liter, and you'll get this concentration of your potassium dichromate. And this is actually used in wines. They react the wine, a sample of wine, with potassium dichromate solutions of known concentration in order to figure out the alcohol content of it. The chromate will undergo an oxidation reaction with the ethanol in there, and it will change color. And so when it goes from a yellow to orange color, and when that conversion is complete, you'll know that there's no more ethanol in there, and that means you've figured out the equivalence point of the titration for that wine and can calculate its concentration or alcohol content. Typical blood serum is about 0.14 molar sodium chloride. What volume of blood contains a milligram of sodium chloride? So if we have mass, here's let's say 1 milligram. I'm going to write it as 0.001 grams because obviously, again, we're going to need mass in grams because molarity in molar masses use, the proper units. So how much blood, what volume of blood contains a milligram? So again, we had molarity is mass divided by molar mass times volume. I'm going to move the volume over there and the molarity down there because you're multiplying both sides by volume and then dividing both sides by molarity. So you get volume is mass divided by molar mass divided by molarity. All right, so we have 0.001 grams divided by the molar mass of sodium chloride. All right, sodium chloride has a molar mass of 58.443 grams per mole. Again, you have one sodium and one chlorine. Get those values from the periodic table. And the molarity of typical blood serum is 0.14 moles per liter. You'll never see that way in a hospital. They do it by the mass per volume percent, which is about 0.9%, but in molarity, it's about 0.14 or 15. All right, so 0.001 divided by 58.443 and divided by 0.14 comes out to 0.00012 liters. All right, grams canceled out, moles cancel out, and you're left with liters in a denominator within another denominator, putting it up in the numerator. That's a terribly, impractical value to use. So let's multiply that by 1,000 to put that in milliliters. All right, this is 0.12 milliliters. Even that's not practical. Well, because do any of you have a concept of a tenth of a milliliter? It's kind of a small amount. But I'll tell you this, 20 drops of water is nearly equivalent to 1 milliliter. So if we have this there, 1 milliliter is 20 drops. You're multiplying by that 20, and you get about 2.4 drops of blood. If you're assuming the drop of a blood is the same volume as the drop of water, 2.4 drops of blood is going to contain about a milligram of sodium chloride. You should be able to visualize 2.5, whatever, drops. How do you get 0.4 drops? Well, don't worry about it. All right, now section 8 here, diluting solutions. There's stock solutions and standard solutions. All right, stock solutions are defined as solutions that you would purchase that have a known concentration. They're usually saturated solutions, and you're going to use those to make less concentrated versions. So you can save money by buying in bulk in a sense, but you're not only buying in bulk, you're buying concentrated in bulk, right? If I had a solution that was 1 molar and I needed to use a solution that was 3 molar, it's kind of hard to get that. I could add some of the solute to the solution, but if I needed to make the solution, why would I have made 1 molar in the first place if I could just add more to it, right? So that's not really practical. If you have a solution, you bought it, most of the time you buy it already made, so you're just ready to use it. Specifically stock solutions like hydrochloric acid. HCl is a gas at room temperature, so can you buy a gas? You could buy tanks of gas, but HCl is an acid, so it's corrosive and eats away at metals, and gas tanks are metals, so that's not practical either. So you just buy it as a stock solution. Stock solutions, again, will be defined as a highly concentrated solution. Doesn't mean it's saturated, but usually they are used to make less concentrated solutions by dilution. Oops. And then the standard solutions will be just solutions that have a very well-known concentration. They could be stock solutions, or they could be dilute. They could be whatever, but they have very well known. When we did our titration in lab, we had a standard solution of EDTA that we used. And, it was measured by just taking a mass of the EDTA and, using the balance to get a very precise mass for that, and then dissolving it in a very precisely determined volume in those volumetric flasks at 250 milliliters, you may remember. So you have a precise mass, you have a precise volume, you can get the concentration to be very well known or standardized. You could use a stock solution to make the standard solution. That is certainly a possibility. But the standard solutions are going to be used to do the reactions with. You have it very well known. If it's an acid-base reaction, it would then go on to react with something. If it's a base, you'll react it with an acid. If it's an acid, you'll react it with a base, because you have its concentration known, and you can determine when the reaction was complete by using a pH indicator or something like we did. You can figure out how much of the unknown material you had in your mixture. If you need to dilute a solution, let's say you're taking a stock solution of, let's say, 12.1 molar HCl, that's concentrated hydrochloric acid, meaning as concentrated as it gets, or it's saturated, but you need to use something that's like 0.5 molar HCl, and you might have a write-up for the lab saying you need to use 100 milliliters of this. How much of the stock solution do you need to use? Well, we can use the dilution equation. If we look at the units here, we have molarity times volume, M1 V1 equals molarity times volume M2 V2. Molarity is moles per liter and volume is liters. Those cancel out the liters to give you moles. When you're diluting, a dilution, you just add solvent. We're not changing the amount of the solute in there. Okay, so if your solvent is water, you just add water. I'm sure if you've ever made something like Gatorade or Kool-Aid, you got to get the concentration just right for it to taste the best. You have not enough water, you get this thick, syrupy mixture, and it's, almost too potent, too sweet, or too salty, or whatever. It's not going to be that good. If you had way too much water, it's actually just worse than water, and it's worse than the Gatorade or Kool-Aid for whatever reason, at least in my opinion. That would be too dilute. So you got to get it just right. But either way, the amount of stuff you've added to the mixture, the solute, the Gatorade powder or the Kool-Aid powder, should still be the same, whether you've over-diluted it or under-diluted it. All right? But in this case, let's say we wanted to do this. We take 12.1 moles per liter times some volume of it, and we want to end up with 0.5 moles per liter, and then end up at 100 milliliters or 0.1 liters. So those cancel out there. All right. And, well, we can move the 12.1 over there to say V1 is going to be M2 V2 over M1. So we get the 0.5 times the 0.1 divided by the 12.1, and so this will be, let me get my calculator out, 0.5 times 0.1 divided by 12.1, and we get 0.004 liters. That's obviously stupid to use that. Nobody knows what that means. So multiply it by 1,000 to put that into milliliters. and your initial volume would be 4 point, let's just, whatever, we'll put 4.1 milliliters. So you take 4.1 milliliters of this highly concentrated solution and you dilute it to 100 milliliters, you'll go from 12.1 molar to 0.5 molar. That is a dilution equation. And then the final slide here, you're given a solution of 14.8 molar ammonia, NH3. How many milliliters of this solution do you require to give 100 milliliters of 1 molar ammonia when diluted? So M1V1 equals M2V2. How many milliliters do we require? And again, this is V1. So V1, we just divide both sides by M1. And we get M2V2 over M1. Our final concentration, we want 1 molar, 1 mole per liter. Our final volume, we want 100 milliliters, or 0.1000 liters, divided by our initial concentration, 14.8 moles per liter. I'm going to cancel out the whole moles per liter there, and you see there's a volume left over. So volume 1 is 0.1 times 1, which is 0.1, divided by 14.8, and this ends up being 0.0067, and we have 3 sig figs, so 676 liters. Again, you're going to multiply that by 1,000 because it's impractical to use liters, so this ends up being 6.76 milliliters. You take 6.76 milliliters, you dilute it to 100 milliliters, and you go from a concentration of 14.8 all the way to 1. So in some ways, this is the convenient way to make your standard solutions. You buy a stock solution as concentrated as it gets, saturated or concentrated, and then you just add water to get the concentration you need. This was actually one way Walmart, let's say a decade and a half ago, really changed the paradigm on shipping costs, specifically for things like laundry detergent. When I was younger, they would sell laundry detergent at concentrations that were usable in washing machines at the time. And then they realized, well, these things are huge and they're heavy. They're full of a bunch of water. Why don't we just make them more concentrated? They made them less dilute, and all they did was they just didn't add as much water. That makes the packaging smaller. It makes the mass of the unit smaller, and therefore they could fit more of these laundry detergent drams in a truck to ship, and therefore save tons of money on shipping costs. They literally saved billions of dollars in their first year after doing this. You might have been too young to even care or know at the time when this happened, but this was part of the shift from just regular detergent and regular washing machines to the high efficiency washing machines and high efficiency laundry detergent, because it's much more concentrated now, and therefore you're wasting less water. You shouldn't have to pay for water. In reality, you could just buy powdered laundry detergent, solid powder, and you're not paying for any water. And you go to a grocery store, they still sell those, and it's way cheaper by volume or by the amount of uses you get out of it than the stuff with water, because ultimately shipping costs and production, they got to take the solid powder, add water, add dyes for sometimes, and perfumes and stuff like that for people that want those things. So it just ends up costing more money. But do what you want, buy what you want. That's it for today's final lesson in chapter 4.